Okay, so our next speaker is Joshua Feinberg from University of Haifa. So he'll talk about density of eigenvalues in a quasi-Hermitian random matrix model, the case of indefinite metric.
So thank you. I thank again the organizers for inviting me and for organizing such a nice and friendly conference. So I will talk to you today about a combination of a vast field in mathematical physics, namely random matrix models, which has connections to India, for example, due to Madan Lal Mehta, who was one of the gurus, literally, of this subject, and with the PT-symmetry, PT quantum mechanics. Okay, so let's. Oh, what's going on? Ah, okay. So this is the outline of my talk. I'm not sure I will be able to cover everything, so I will go through the first few chapters and then jump to the. Where is the laser? Which one? Oh, this one. Okay. Thank you. So, what's going? So I will go through the first few chapters and then rush to the end. And then, if I have any time left, I will complete the chapters. Okay. So this is the outline. I will start with a simple definition. I will give you a very nice and very simple mechanical example, which you could take to your classes if anybody teaches analytical mechanics and small oscillations. I mean, you can actually tell this to your students. Oops. Then I will make the distinction between strictly quasi-Hermitian matrices. I mean, when the metric is positive, and also when the metric is not. Then I will discuss random matrices, how to make all this to put this all into random matrix theory. This is a long chapter that I don't know if I will have time to review about the methods which you actually use to calculate things in random matrix theory in this context. And finally, I will give you an example for matrices which are random and also a Hermitian or satisfy the intertwining relation or the Dieudonné relation with respect to this indefinite metric. So you have some metric with pluses and minuses, and there are interesting analytical and numerical, consistent numerical results for this model, which I would like to describe and then come back to whatever I missed if I have any time left. Okay. So I define strictly quasi-Hermitian matrices. Oops. In this way. So let's say we have a metric, a positive metric, M. Then a complex matrix is strictly quasi-Hermitian with respect to M if it fulfills the intertwining relation. Everybody knows that, but for the record, here it is. Of course, when M is the unit matrix, you are back to the usual Hermitism. So, well, the intertwining relation just tells us what was mentioned in Ali's talk a few minutes ago, that H is Hermitian with respect to non-trivial metric. Now, the general solution of this intertwining relation is very simple, actually. If H satisfies this relation for a given M, then the solution is H equals an Hermitian matrix times M. For example, you can see this in this paper by Yogesh. Then, given a metric, you can find n-square independent, strictly quasi-Hermitian matrices with respect to this metric. Just choose all the, just choose a basis for these Hermitian matrices, and then for each one of them you get an H. So, of course, as everybody knows, for positive M, the spectrum of H is real. since H is similar to a Hermitian matrix. And here is the similarity transformation. Now I should also mention in passing that numerical investigations, not only of the distribution of eigenvalues, but also of the fluctuation, the statistics, for example, the distribution of level spacing was studied numerically in this paper by Yogesh et al., which I mentioned. And also I learned a few days ago from Pijush that they studied a similar problem of level spacing in a PT-symmetric random matrix theory as well in this paper. And also a recent paper by Kumar and Ahmed. I thought they would be here, at least one of them, but apparently they haven't come here. Okay, so now in general, let's make the distinction between strictly quasi-Hermitian and quasi-Hermitian. So if I lift or relax the positivity of M, then I'm facing quasi-Hermitian matrices. Okay, so just think of M as an invertible matrix, not necessarily positive. Still, the solution of the intertwining relation is the same, with no change, but since the square root of M is no longer Hermitian, because it's not positive, then this small h, which used to be a Hermitian matrix, is not can possibly not be Hermitian as well. I mean, if the overall phase of square root of M is I, then H will be Hermitian, but in general it needn't be. So quasi-Hermitian matrices, as opposed to strictly quasi-Hermitian matrices, may have pairs of complex conjugate eigenvalues because their characteristic polynomials has real coefficients. This you can see from the intertwining relation. From the intertwining relation, you see that this holds, and therefore the coefficients of the characteristic polynomial are real, and therefore the complex roots come in pairs. So let's now go down to Earth and think of very concrete, simple mechanical problem, namely small oscillations about some stable fixed equilibrium point. So everybody knows this equation for small oscillation, where M is a matrix. I mean, we assume we have a system with S degrees of freedom. This is the Lagrangian in general. Okay. Okay, so you have Q is a set of generalized coordinates. You have the kinetic energy with some metric. You have a potential. You have an equilibrium point. These are the deviation from equilibrium, and you can expand this around the equilibrium. M is just the value of the metric at Q0, and K, the matrix K, is the Hessian at the equilibrium. I'm not telling you anything you don't know already, just for the record and definition. So we shall refer to M as the mass matrix and K as the matrix of spring constants. Okay, and this is the equation you tell your students to solve. So you look for harmonic eigenmodes of this form, and you plug it into the eigenmode equation, and you look for the roots of the characteristic polynomial. Physically, of course, small oscillations about a stable minimum has so all frequencies have to be real. Therefore, all omega squares have to be positive. I mean, all the roots have to be positive, and this is clear because if you choose a particular mode with its amplitude, then you can see that omega square has to be real, positive, of course. Now, there is another way to see this positivity, because you can rewrite the eigenfrequency equation in this way. And since M is positive, all masses are positive, then square root of M is well defined. For example, I take the positive square root of M, and therefore, you see that the matrix which we are diagonalizing is this matrix, which is manifestly Hermitian and positive. I mean, it's manifestly positive. And, okay, so therefore all its eigenvalues are positive. Okay, but let's let's kill this problem, really overkill it, and rewrite the eigenmode equation in this way. Okay. So we have a matrix 1 over m times k, which I call H, and our task is to diagonalize it and to find its eigenvalues and prove that they are all real. They are all positive. Now, if this is H, then this is H dagger, and clearly they are not the same. However, you see that H fulfills the intertwining relation with respect to the metric. H dagger m equals mh equals k. And equivalently, H dagger is similar to H. So H is an example of strictly quasi-Hermitian matrix with respect to the metric M. And it is similar to the positive metric small h, which we discussed earlier. So this is a neat, nice, pedagogical example, which you can use in your classroom. So now, obviously, we had two matrices, H, K, and M. So we can now turn this into a random matrix problem. I mean, we can randomize everything. And you can use this approach of randomization. I mean, this is the general ideology of random matrix theory, that you can use it to describe very complicated systems that it makes no sense to study each and every particular energy level or eigenmode, but rather to specify the statistics of these things, like what Wigner did with neutron resonance energies in complex nuclei. I mean, it's such a complicated system, there's no point in studying each and every level. So for large systems, for large S, many degrees of freedom, which are connected with this big connectivity, with high connectivity. I mean, everything is connected to everything else, so you are dealing with full matrices, not structure matrices. So this problem naturally lends itself to analysis in terms of random matrices. So we draw matrices M and K from sensible, uncorrelated probability distributions of positive definite matrices, and compute the resulting eigenvalue statistics of this matrix. So there is a machine to do that in the business of random matrix theory. It's called free probability theory. Free probability theory is the probability of random variables which do not commute and are independent. So it's a theory invented in the early 90s by mathematician Voiculescu and his collaborators. And this formalism has a machine called S-transform. And with the S-transform, the so-called S-transform, I don't want to describe it. I don't want to get into it, just want to mention it. You can, given the spectral properties of M, the average spectral property, the statistical properties of M, the statistical properties of K, you can find easily what the distribution of eigenvalues on average of H is. This is a paper which should appear soon, so I just mentioned it here. Now, let's go to indefinite metric. So first, let's give some physical and mathematical motivation. I mean, as if somebody needs motivation in this community, but nevertheless, again, let's give some motivation. So going back to the mechanical problem I just described, you can imagine some of the masses in the system for some reason become negative. You can think about bizarre physical situations like that. So the metric becomes indefinite because M was the metric in the previous formulation. Now I can change the roles of M and K and write the equation in this way. It's the same equation, but now I consider K as the metric. So equivalently, I can think of situation, and this is by the way physically more viable. I mean more probable that some of the springs becomes unstable. I mean they develop tachyonic, so to speak, tachyonic modes. So this also leads to a matrix problem with indefinite metric. And if M and K are big and complicated, you can treat them as random. Therefore, you have random matrix theory for non-definite indefinite metric. Another nice example, not exactly of quasi-hermiticity or pseudo-hermiticity, but anti-hermiticity, which is the same up to an I, is to consider the generators of the classical non-compact groups, either orthogonal or unitary or whatever you want. I mean, you can use other, but let's concentrate on the orthogonal and the unitary. So the defining relation, you have a metric. Here is the metric. Some number of pluses, let's call them n, and some number of minuses, let's call it m. So if you are talking about orthogonal groups, this would be O and M. Our beloved Lorentz group is O31. So the defining relation for this group is that an element of the group has to satisfy this relation. And if you consider infinitesimal generators around the unity, epsilon, then this leads to this, which is the intertwining relation for anti-symmetric matrices, and you can solve it by substituting epsilon equals some anti-symmetric matrix times M. That's the solution. You can check it. So any generator of O and M, of the Lorentz group, for example, is a multiple of an anti-symmetric matrix times the metric. Same thing for the unitary groups. Here is the condition. Go to the infinitesimal generators. This is the intertwining relation for anti-Hermitian, anti-quasi-Hermitian matrices. And the solution is, again, any infinitesimal generator of U and M is an anti-Hermitian matrix times the metric. So now you can ask statistical questions. I mean, if you're dealing with very big groups, I mean, large N and M, for example, then you may ask, what is the probability if you just take a generator at random? What's the probability that you have so and so many complex eigenvalues or no complex eigenvalues? There are meaningful questions. For example, to consider whether the, well, okay, it's an interesting question. Let's not elaborate an obvious thing. So, so that's the second motivation. And the third motivation, and I'm sure there are many more, is studying the PT-symmetry breaking transition in a quantum system, but defined in a finite dimensional Hilbert space. So you deal with n by n matrices, and essentially this phenomenon happens because the metric stops being positive definite. So you can use random matrix theory to study some statistical properties of very big finite dimensional systems. And similarly in optics, I mean, because of this mapping between paraxial propagation of waves and PT-symmetry propagation in gain-loss balance, etc., etc. So random matrix theory is a very useful tool to describing complicated or complex systems of this sort. Okay. So now let's talk about quasi-Hermitian random matrix theory for a fixed deterministic metric. So a fixed metric, it's not fluctuating, it's deterministic. The only thing which fluctuates is the Hamiltonian. Okay? So this will be in a paper which will appear with my postdoc Reiser, Roman Reiser in Haifa. So I'm going to tell you some results from this work. So I have about 20 minutes. Okay. So let us consider some n by n random matrix, okay, and a fixed deterministic metric P, which is Hermitian. It can be positive definite, it may be indefinite, but it has to be Hermitian. And we have the intertwining relation. So phi cannot be anything that we like, but it has to satisfy the intertwining relation. As I told you before, the general solution is always of this form, with A being a Hermitian matrix. So B is fixed, it's deterministic, the only fluctuating part is A. So we can choose A from one of our favorite ensembles of Hermitian matrices. This is a well-trodden territory, but I, like Robert Forst, now use it to take the road untaken, namely those Hermitian random matrices. So, so I draw A from my favorite probability ensemble, let's say something of this sort, which is invariant under unitary rotations, because unitary invariance is very useful, it's very convenient, and it also lies at the base of free probability theory, which I mentioned earlier. Not that I'm going to use free probability theory, but just mention it. So, and for simplicity, because we just want to demonstrate a concept, let's take the simplest such ensemble, namely the GUE, the Gaussian unitary ensemble. Just Gaussian Hermitian matrices distributed in this way. N is the size of the matrix. By including N in the exponent in front of the trace, it means that every element of the matrix is typically of the size of magnitude 1 over square root of N. And because of that, the eigenvalues will be contained in the finite segment. I mean, the semicircle, Wigner's famous semicircle, will be finite rather than square root of N size. And the reason is that when you write down the eigenvalue equation, this, for example, for the ith component, this is a sum of n fluctuating numbers. So by the central limit theorem, it should be of the order of square root of n of whatever the typical size of psi is. And if the typical size of psi is 1 of square root of n, then the typical size of the left-hand side will be 1, and therefore the eigenvalues will be typically of order 1, and not of square root of n. So that's why, oops, what happened? Oh, I'm going the other way. Yeah. Oh. Okay, so that's why I put a factor of n here, and m is just a scale factor to determine the width of the semicircle. Z is a normalization constant. So I'll take my A to be GUE. And of course, it is invariant under unitary rotation. P of U is the same as P of U, A, U dagger, where U is unitary. So since P of A is invariant under unitary rotations, I can, with no loss of generality, assume the metric B to be diagonal, because I can always absorb the unitary matrix which diagonalizes B into the random part, and it doesn't change the probability. I mean, A and rotated A have the same probability to be drawn, so nothing changes. And my goal is to calculate the average eigenvalue density. At least my initial goal is to calculate the average eigenvalue density for the quantum Hermitian random matrix phi in the Largent limit. In the Largent limit, which offers some simplification. A further goal, which I didn't put in my slide, is to study correlations between eigenvalues and the level spacing statistics, but this is much more difficult. Okay. So, the spectrum of eigenvalues of H, of phi, can be read off the resolvent, from the resolvent of phi, okay, from this object. Average, the brackets here means I average over the GUE ensemble of A. Now, there are fundamental problems or difficulties when one comes to analyze the spectrum of non-Hermitian matrices. I mean, analyzing Hermitian random matrices is well known. There is an arsenal of tools, very efficient tools and strong tools, but all these tools are helpless, useless, when you try to apply them directly to non-Hermitian matrices. So one has to think about strategy, how to overcome these difficulties. So let me try to explain to you what the difficulties are. Okay, maybe. Okay, 15 minutes. Okay, so Okay, at this point, I think I shall skip and then come back to this point later. Okay, sorry. Okay, now unfortunately I can't do it in one swoop. So I give you a tour. Obviously, I'm not going to be able to cover everything. Okay, so as I said, my example involves this metric. It's like one of those metrics for the orthogonal, I mean for the non-compact orthogonal or unitary matrices. So we analyze phi with this metric, A, G, U, E, and phi, and B given by this fixed metric, with k positives and n minus k negatives. And let me show you, let me state the analytical results in the Largen limit, of course. So as I said, we consider k positives, but in order to see this in the Largen limit, you have to take k to be a finite fraction of n, otherwise you will not see it in using the Largen method. We could do k equal 1 on 2 by other methods, but you cannot really apply these methods for higher case. So it gets excessively complicated. I'm not going to show you k equals 1. Anyway, so we assume k is a finite fraction of n. So lambda, the fraction, is some number between 0 and 1. When lambda is not at the ends, I mean neither 0 nor 1, okay. The Green's function, which I wrote, which I showed you earlier, where is the, oh, this one. This Green's function. Despite the fact that you see the variable w here, when the spectrum of AB is complex, this quantity is not an analytic or holomorphic function of w. It actually depends on both on w and w star. So when G is non-analytic and therefore has non-holomorphic dependence, I call it the non-holomorphic solution. And when G is analytic, I call it a holomorphic solution. Non-holomorphy appears whenever the eigenvalues, if you have a blob of eigenvalues in the complex W plane, if the eigenvalues occupy some two-dimensional blob, some region in the complex plane, in this region, G will have W star dependence, okay? However, if eigenvalues live only on the real axis, then when you go off the real axis, G will be holomorphic. In other words, when W is located where there are no eigenvalues, G is holomorphic. And this comes from the Gauss law, so to speak. I mean, I can think about G as the electric field. If I think of the eigenvalues of the matrix as some point charges in the complex plane, think about formulating electrostatics in 2 dimensions in terms of complex variables. So G would be just the electric field, and this is Gauss' law. No? So obviously, when G is holomorphic, this is 0. You don't have any eigenvalues. So again, when lambda is not 0 or 1, you have both holomorphic and non-holomorphic regions for G. This means that simultaneously, for any such lambda like this, you have regions. You have some regions in the complex plane where you have complex eigenvalues, and also there should be eigenvalues on the real axis. So the eigenvalues split. Some go off into the real complex plane, and I must say in a symmetrical way, because we agreed already that the characteristic polynomial is always, I mean, it has real coefficients. So complex eigenvalues come in pairs, conjugate pairs. So there must be two mirror, the eigenvalue distribution in the upper half plane has to be a mirror image of the one in the lower half plane. So in these blobs, the G will be non-holomorphic. And if you go out of those blobs, the G will become holomorphic with possibly eigenvalues on the real axis. Now, another fact that we proved or established is that the density in the Largen limit in the two-dimensional blobs, the density is always constant. I mean, the eigenvalues cover it uniformly. And with a density which is independent of lambda. And at the edge of the blob, the density drops sharply from rho, finite value rho, to 0. So this is proved analytically. Now the boundary of the blobs, of these blobs, is given by this nice equation. R and theta are polar coordinates, and sine theta naught is given by lambda in this way. So you see it's between -1 and 1. And if you demanded the discriminant of this thing will be, of this equation for R, will be positive, it means that sine theta square has to be bigger than sine theta naught square. And this means that you have two arcs or two sectors in the complex plane, one in the upper half plane and another one which is a mirror image of it in the lower half plane, where these curves live. Okay, and you can solve the quadratic, quartic, I mean, and you find the two roots. The bigger one is the one with the plus. The smaller one is R minus. And in a minute, I will show you a figure. R plus, as I said, is part of the boundary farther from the origin, both up and down. I mean, in the upper half plane and in the lower half plane. And R minus is the arc that is closer to the origin. And since the discriminant vanishes here, this is where the two arcs match and make a close contour, where they are sewed together. Okay. Now the gap between the two blobs. So what you get is something like this. Sorry, I'm erasing this out. So what you get is something like this. This is W space. You will see it immediately. You get two blobs like this and some eigenvalues living here. And so this would be R plus of theta. And this would be R minus of theta. And this would be theta naught. Actually, pi minus theta naught. This is 2 pi minus theta naught. This way. And you see that the two curves match here at these points where the discriminant vanishes. And the distance between them is twice the minimum of R min, namely this. That's the distance of the gap between the two blobs. It's given by this expression. And you see that the two blobs kiss. I mean, they close together when theta naught is 0, i.e. when lambda is half. So remember, when lambda is half, these two blobs come together and kiss here. They close, and you get one. You actually get one domain. That happens at lambda equal half, namely half the matrix is plus, half the matrix is minus. In this case, R plus for lambda half, R plus is just 1 over m. And in the complex plane, and this is exactly what you would have in the case of the famous Ginibri ensemble of complex matrices. In Ginibri, when you take a complex non-Hermitian matrix taken from this ensemble in the Largen limit, the eigenvalues will cover a disk of radius 1 over m in a uniform way. So this model, in the case of lambda equals half, namely half the matrix plus, half the matrix minus, just gives you a distribution the same as Ginebris. Okay, and the densities, since they occupy the area, since the eigenvalues, all the eigenvalues occupy this disk, this circular disk, with this given radius, then the density is just this. Okay, and this is exactly Ginebris density. And it's independent of lambda, so I can use this value for any lambda, because the constant density is independent of lambda. I can calculate the area. I can calculate the area of each of these blobs. Yeah. So this is the area. Sorry, this is theta naught minus pi. Yeah. So I calculate the area encircled by this blob, and you find it's pi lambda over m squared. Then I take twice this area and multiply it by the density which I just showed you. And then I find how many complex eigenvalues live in, how many complex eigenvalues there are, the fraction thereof, which is just this. And I stress that this result holds for lambda smaller than half. For lambda bigger than half, I have to shift. Lambda goes to 1 minus lambda. And the reason is, namely, k goes to n minus k, and this is because in the intertwining relation, it doesn't matter if I multiply b by minus 1, or by any phase for that matter, but multiplied by minus 1 is just equivalent to this. So it doesn't change the statistics of phi. Okay? So now let me show you. So in other words, we have established that the number of, or the fraction of real eigenvalues is 1 minus 2 lambda. The fraction of real eigenvalues, is just 1 minus 2 lambda. So now let's check it. Let's ask Mr. Computer and see what happens. So here you see a black line. The black line is just 1 minus 2 lambda absolute. Okay? And the red dots are simulations for matrices of size 128. The blue dots, which are very, 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 very dense, they're almost a continuum, hard to resolve on this figure, are for very big, rather big matrices, 1024. And you can see that they match very nicely with the theoretical curve, except a little bit finite end corrections near the symmetric point. So that's nice. And here are some scatter plots for fixed lambda, but different values of n, because I want to demonstrate to you how the system converges to the large n limit. So for moderately sized matrices of size 128, for B with 32 pluses, namely lambda a quarter, and 200 samples, we get this. This is the scatter plot of the eigenvalues. So you see we have eigenvalues on the real axis. We have the two blobs that I mentioned. The black curve is the theoretical curve I showed you earlier. So you see the two symmetrically blobs. It's two symmetrically positioned blobs, and you see that essentially the bulk of the spectrum is within the predicted domain, and there is a little bit of scatter because of finite n. Yeah, I'm almost done. Okay? And this is for a bigger matrix. You see there is less noise, and here is yet for a bigger matrix, 32,000. So you see almost no fluctuations out of the perimeter. And for lambda equals half, as I promised, the two blobs kiss and form one happy disk. Okay, so again, 128, 1024, and 32,000. And here are some 3D histograms of the eigenvalues. And you can see roughly the lambda goes to 1 minus lambda symmetry. You see these are the eigenvalues on the real axis. This is the blob, and it's roughly the same. Here again, here you see, I think here you see some difference. I mean, but this is probably a binning problem. We have to figure it out. It's probably a binning problem of the data, but roughly speaking, it's the same. Here is the full disk. You see a little bit of enhancement on the real axis, but this is typically also in Ginibri's case. If you look at Ginibri's real ensemble, I'm done. There is a little bit of enhancement on the real axis because square root of 1 over n fraction of the eigenvalues coalesce there. But in the large n limit, you will not see it. I mean, this will disappear. This reach will disappear for very large n. And here are histograms for the eigenvalues on the real axis. You see, it's not a semicircle. You see a double hump or dumbbell. Again, some similarity between lambda and 1 minus lambda. And if all eigenvalues are positive, of course you get. I mean, B is just unit metrics. Of course, you get Wigner's semicircle. This is for 128. So that's it. Thank you.
Since we are already running out of time, so let's continue the discussion afterwards. Okay.
Thank you.
So let's thank both speakers again in this session.